Hello, everyone. Welcome to another sessions at the Data Science Summer School. And my name is Hui Dang, and I'm the manager at our Data Science Lab here at the Hertie School. The Data Science Summer School is our annual effort to contribute to the open source communities by opening up scientific learning for the general public. And we are very happy today to see so many of you from so many different countries, so many different disciplines and industries joining us here today. And we're very glad that you have decided to spend your precious summer month with us. One of my colleagues said that, which I think is very true, that when we're children, we hate summer school and all we want to do is play. But as adults, it seems that we are actively seek out these kind of opportunities like summer schools so that we can improve our skill set, which I think is quite funny and also true. But of course, as children, we have different priorities. And our summer school today is made possible with the generous support and funding from the Hertie School and the Digital Foundation in Germany. And I'd like to thank them for their continuing support for our summer school going forward. And our session here today is linear algebra for data science, which will be led by Surpresim Sadiku. And he's currently a PhD candidate at the Institute of Mathematics at TU Berlin. And he's also affiliated with the Interactive Optimizations and Learning Research Lab at the Zeus Institute Berlin, where he holds the scientific assistant positions. He received a Master of Science in Mathematics and Data Science at the Technical Universities of Munich and a bachelor degrees in mathematics at the University of Tirana in 2017. And Surpresim, the floor is now yours. I hope everyone will have a good time and also enjoy learning about some math today. Thank you very much.
Okay, thank you very much, Hui, for the very good introduction. So first of all, I will start sharing my screen. All right, so today's session is going to be about linear algebra for data science. And I would like to take this moment to thank you once again for inviting me to do this workshop. It's truly an honor to be in front of so many people who are eager to know about linear algebra for data science. My name is Surpresim Sadiku. This is my email over here, where you can contact me about any questions that might arise later at some point. This is my personal website. This is where you will also be able to find all the materials from today's workshop. As you said, I'm a PhD candidate in mathematics at the Technical University of Berlin, and I'm also a scientific assistant at the Zeus Institute Berlin. I am very passionate about artificial intelligence. I think it's very interesting how this new technology is revolutionizing the world in many areas. And whenever scientific fields appears to be working so well in practice, we also want to know, in theory, why does it work so well, and also explain its decisions that it's doing. So my main area of research is actually the robustness of such techniques and their ethical concerns. Apart from artificial intelligence, I'm very passionate about traveling and fitness. So this is my passion outside of academia. All right, so you might want to question, why do we actually care about data science? And at the beginning, I just want to give you some really simple examples about what data science is actually capable of doing. For example, one very prominent example in computer vision, it's image segmentation. So we are given an input image, which may contain some objects like we have here with the cats. And what we want to do is that we want to simply remove the parts which contains the main items of this image, which in this case is the cats. So we want to do image segmentation, and this application is actually way more important, for example, in cancer research, where we are able to analyze MRI images, and we are able to use techniques from compressive sensing to actually detect whether whether cells are benign or malign. Then another application is, again, in object classification. So we are given an input image, which just contains some object. And then we want to use some technique from data science. So in this case, we are using gradient boost and confidence boost. So one of them is showing that this object is a lemon and the other one that it's a lime. So there are a ton of techniques that one can use for classifying items, but the state of the art nowadays is neural networks, so deep learning. Another application in data science is 3D shape analysis or shape retrieval. So this is, for instance, used to find like the movements of a person in this case. I mean, there are applications, for example, in detecting terroristic attacks or something like that. Or we also have optical character recognition. I think we are all aware of this application. So whenever you try to download an app or whenever you try to log in to somewhere, you are usually required to do some optical character recognition, and this can, again, very well be done by artificial intelligence. And we have also seen how data science has also revolutionized the e-commerce, Netflix, Google AdSense. So these are all applications that we use in our everyday lives, like machine learning or like optimization is used everywhere to optimize the routes of transportation. So this has helped with optimizing the CO2 emissions of transportation vehicles. And then we've seen the recommendation system, which first went live in Netflix, but nowadays is using throughout all the social media platforms to recommend content which is very close to what someone wants to see. Okay, so we have all these applications of data science, but then for one to be able to do data science, there is required some mathematical background. And usually the three fields involved in artificial intelligence or in data science are linear algebra, which is a workshop that I will give today. The second one is calculus, which will be tomorrow again by me. And the last one will be in statistics and probability theory, due on Friday. And actually, these three mathematical areas are very related to each other, but they are actually also studied in isolation when one wants to do data science. But in order to be able to understand and to be able to do data science, I believe that one should have a solid background in both the three areas. All right, so just to give a brief outline, we will first start with giving some basic notation, then we will see matrix multiplication. So here we will talk more about how do vector-vector products work. We will see how matrix vector products work, matrix products, and then we will see some more operations and properties from linear algebra. So we will see the identity matrix, which is used a lot in data science. We will see diagonal matrices. We will see the transpose of a matrix. We'll talk about symmetric matrices, the trace of a matrix, norms, which are very much used, for example, when one wants to study adversarial attacks. So you want to have images which have a certain LP norm, for example. Then we will see linear independence and rank of a matrix. We will see how do we compute the inverse of a matrix. We will talk more about orthogonal matrices. We will see the range and null space of a matrix, the determinant of a matrix, and then we will see some quadratic forms and positive semi-definite matrices. Then we will talk about eigenvalues and eigenvectors. And finally, we will see how do we do eigen decomposition. So when we find eigenvalues and eigenvectors, this is called eigendecomposition of symmetric matrices. All right, so I would like to begin on why do we actually care about linear algebra? So we usually use linear algebra to compactly represent and to operate on sets of linear equations. So linear algebra provides a way to compactly do such a representation. And for example, we have this system of equations for x1 minus 5x2 equals minus 13, and the second equation minus 2x1 plus 3x2 equal 9. So these are just two linear equations, and we have two so-called variables, which are x1 and x2. And as I hope we all know, we are able to find a unique solution for x1 and x2 unless the equations are somehow degenerate. So for example, if the second equation is a multiple of the first equation, but in this case, we don't have such a degenerate case. So in this case, we are able to actually find a closed form solution for this equation. And we can express such a system of linear equations also in matrix form. So AX equals B, where A is just a matrix containing 4 entries, 4, minus 5, minus 2, and 3, and B contains minus 13 and 9. We will actually shortly see that there are many advantages, which also includes the obvious space saving to such a representation, as opposed to having the representation which we had here at the beginning. So, okay. All right. All right, so we can start with some basic concepts and notation. So we will start by simply letting A denote a matrix with m rows and n columns. So all the entries of A are actually real numbers. So in this case, the A would simply look something like this: A11 to A1n, and then we would have am1 to amn. All right, so we have m rows and n columns. And then this is the notation for a matrix. X, on the other hand, in Rn, will simply be a vector of n entries. So in case we are talking about a column vector, then this is simply a matrix with n rows and with 1 column, as we have depicted here, actually. So this is just a matrix with n rows and 1 column. But we can also write this in a transposed fashion. So when we bring this down, then this could simply be x1 to xn. All right, and why do we actually care about vectors and matrices? Well, vectors and matrices are used in data science a lot. Actually, for example, if we have some data record for the square footage of a house containing some certain square feet and its evaluation in dollars, let's say, then we could simply express this as a vector containing 2 entries, where the first entry would be the square footage, and the other one would be the price of the house. And this is then a way to compactly represent a lot of data that we are typically dealing with in data science. So yeah, the main purpose of a vector is to visually represent a piece of data. All right, so then matrix elements. So entry of a matrix A in the ith row and the jth column is simply Aij, or we can write this also as a capital Aij or Ai comma j. And then we can also denote this more compactly by denoting the jth column of A simply by ij or I dots comma j. So this would be when we want to represent with columns, or if we want to represent in terms of rows a matrix, then this would be the third representation that we are showing in the slide. All right. But usually you can also write this in terms of transposes. So you just, these definitions are sometimes a bit ambiguous, but you also have to know them from the context that you are using them. All right, and where do we actually use matrices? Well, matrices are also used a lot in data science. For example, we see here an application in machine learning. In the first image, we have a one-layer neural network given by a matrix W times the input X. So the input X in this case is just this image of a cat, which is simply a matrix containing 128 by 128 entries. And this is actually the number of pixels. So in total, we have 16,384 pixels. And then how neural networks would come to a classification for such an image, they would simply apply a matrix W of coefficients to this input. And then we would have that in this case, for example, this is the 10th label. It would give a classification for such an image. So this is just a simple application of a matrix. We could also have a two-layer neural network given by this expression. So in this case, we have an activation function. We first apply a matrix W1 to the input X, which is again the image of a cat. And then we apply a threshold. So we want to take all the entries which are bigger than 0. This is so-called the ReLU activation function. And then we apply to this new entry H, we apply a second matrix W2. And we get again the same prediction that would be 10. All right, so this is just to showcase where do we actually use matrices and vectors. But then as soon as we have matrices and vectors, we can actually do operations with them. For example, we could have the product of two matrices. If we have a matrix A in R m times n and a matrix B in R n times p, then we can calculate the matrix C, which is simply the product AB, which is in R m times P. And the formula for computing the product of two matrices is given simply by the sum K1 to N AIK BKJ. So if we want to represent this more in a matrix form, which I think we will actually also see a bit later, if we have this matrix A, this matrix B, then the matrix C over here, one entry, the first entry here would be by just summing up the first row of A with the first column of B. All right. One thing that we have to note here, in order for the matrix multiplication to make sense, we have to take care that the second dimension of the matrix A n in this case has to agree with the first dimension of the second matrix B. Otherwise, we are not able to do actually matrix multiplication. All right, so now that we have the definition of the matrix multiplication, we are actually able to do operations by multiplying multiple matrices. We have, for example, the inner or the so-called dot product of two vectors, x and y in Rn. This is simply a real number given by x transposed y, which is a number in R. And we have a row vector for x and a column vector for y. So this is then just the sum I from 1 to n, xy, yi. So let's say x is 1, 2, and y is 2, 3. Then their inner dot product would be simply, we represent this by this. So 1 times 2 plus 2 times 3, this would simply be 2 plus 6, 8. So yeah, the inner dot product is simply a special case of matrix multiplication. And one thing that we have to note is that x times y equals y times x. So you could maybe check this on your own, but this is actually true. On top of inner dot product, we can also define the outer product of two vectors. So we have x in Rn and y in Rn. Then the outer product is simply a matrix whose entries are given by this expression over here. And by definition, this is simply the outer product of the column vector for x and the row vector for y. So this would result in a m by n matrix. So in case of the two vectors. Is there a question? Okay. So in case of the vectors that we had from before, we would have 1, 2 times 2, 3. And this would be simply a 2 by 2 matrix. So the first entry would be 2. The second would be 3. Here we would have 4, and 2 by 3 we would have 6. So this would be the outer product of these two matrices, which in case are simply two vectors. All right. Then we can also define the matrix vector products. When we have the product of a matrix A, which is in Rm times n, and we have a vector x, which is in Rn, then we can simply define the vector y as the product from A times x, which will be a vector in Rm. So if we write the A's by the rows, so if we have this expression for A and x is simply a vector, then their product would simply be this vector. But there are actually a lot of ways how we can see the matrix vector products, and I think we will see 4 different ways of looking at them. Second way is if we write the matrix A as columns, so this would be just now a sort of vector containing n entries, where each entry is a column vector on its own. And then we have simply the vector x containing n entries. And then we can multiply the first entry of the matrix A, which is the first column in 1, by x1. The second column, so yeah, I forgot. But that these are actually columns, plus the sum of the second column of matrix A times x2, plus the last column of A, an times xn. So in a sense, we call this by definition that Y is a linear combination of the columns of A. We'll see that this linear combination actually will be really important a bit later. Another way how we can look at the matrix products is by looking at them as a set of vector products. So we have again the multiplication of matrices A times B, and we simply express the matrix A containing m rows, where each row is a vector row on its own, and the matrix B we express as a vector where each entry is a column vector on its own. And this will simply give us another matrix where we multiply the first entry, for instance, would be the first row of matrix A times the first column of matrix B. So yeah, in a sense, in a more general sense, the ijth entry of C equals the inner product of the ith row of A and the jth column of B. And we could also represent A by columns, and we could represent B by rows. So as we see here, A now is a matrix containing it's a vector, containing n elements, where each element is actually a column vector. And B in this case is also a vector where on each row we have a row vector for B. And this would simply give us the sum of the AI and BY transpose. So in this case, we say that the product AB is equal to the sum over all A's of the outer product of the ith column of A and the ith row of B. All right.
As a person, there were some questions about what is the difference between the inner products and the outer product?
Well, yes. So in the inner product, like for example here, we end up having just one entry at the end, as opposed to the outer product. We have actually a matrix. So the dimensions of the output are different between the inner and the outer product. So yeah, there are applications where you actually need to multiply them by doing inner product, and there are applications where you need to do the outer product in order to find this matrix. All right, so now we saw 4 examples of matrix products. And then, this will be 2. We have 2 more. So we can look at the matrix multiplication as a set of matrix vector products. So we have the matrix A here, and we represent the matrix B containing P elements, where each of the P elements is on its own a column vector. And then we simply multiply the matrix A by the column B1. So the ith column, which would be somewhere here in general, of the matrix C, is simply given by the matrix vector product with the vector on the right. So Ci equals the product A times Bi. And the fourth and the last representation of matrix products is if we represent A by rows, and if we view the rows of C as a matrix vector product between the rows of A and the matrix C. So as we see here, we have represented the matrix A containing M rows, where each row is a vector on its own, and we have a matrix B. And then we simply multiply each of the rows of A by the matrix B. So the ith row of C is given by the matrix vector product with the vector on the left. So Ci transposed, which would be just in general an element here, is given by the matrix vector product with the vector on the left. So we multiply the matrix B by AI transposed on the left. All right, so yeah, we have this sort of 4 different representations. This is the first, this is the second, this is the third, and this is the 4th representation for matrix products. You can simply use whichever you find easier for you. And as soon as we have defined the matrix products, we actually have some matrix multiplication properties. For example, the first one is that the matrix multiplication is associative, which means that if we multiply on the right the matrix product AB by the matrix C, this is equal as if we were to multiply the product matrix BC from the left by the matrix A. All right, and the proof for this claim is actually really simple. So we start by just taking an M3ij of the product of matrices IB times C. And then we simply apply the definition of the matrix multiplication. One thing you have to know here is that all the dimensions, so the second dimensions of A and the first dimension of B has to agree with each other. And then the second dimension, which results from the product AB, has to agree with the first dimension of C. So this is a requirement. And then we can simply reapply the, again, the definition for we can simply reapply the definition of matrix multiplication for matrices A and B. This is again sum from L1 to N, AIL, BL, K. And then what we do, we simply use the distributive property of matrix multiplication. So we we put the third matrix into the summation, and then we exchange the summation so that we are able to again play the same technique that we did on the first row. So we take AIL in front, and then we have the sum K from 1 to P of BLK C Kj. And this summation by definition is simply the matrix products between the matrices B and C. And then this expression over here, sum L from 1 to N AIL times the product of matrices BC LJ, sorry. This, on the other hand, simply gives us another definition of a matrix multiplication. So yeah, the first and the last two equalities simply use the definition of matrix multiplication. The third and the fourth equations use a distributive property for scalar multiplication over addition, and the fourth equality uses the commutative and associativity of scalar addition. So this technique is actually very famous, and you can also use this to prove that the matrix multiplication is distributive, where if you multiply, let's say, the summation of matrices B and C from the left by the matrix A, this is simply the summation of the product of matrices AB and the product of matrices A and C. However, matrix multiplication is in general not commutative, so the product AB is usually different from the product BA of two matrices B and A. This is very actually easy to see, because if A is a matrix in R m times n and B is a matrix in R n times Q, then you can see that the product between the matrices B and A actually does not exist if M and Q are not equal. So yeah, every time you have to do matrix multiplication, the first thing that needs to be done is to check whether the dimensions agree. All right, so then a very important concept in data science is also the definition of the identity matrix and the diagonal matrices. So the identity matrix I, defined as a matrix in R n times n, is simply defined as this matrix Ij, where it has entries 1 in all the indices where I is equal to j and it's 0 otherwise. So if we want to represent this as a matrix n times n, then we would have something like this. So all the rest would be 0, and here all the rest would be 0. All right, so one property of the identity matrix is that if we multiply the identity matrix from the left by A, this just gives simply the matrix A, and this is also equal as we were to multiply the identity matrix by A from the right. Another very important definition is the definition of a diagonal matrix, which is defined as Dij, where we have an entry Di for all the indices where I equals j and 0 for other entries. So if we were to represent this as a matrix, this would simply be D1, D2, Dn, and all the rest will be 0. So it is easy to actually see that the identity matrix is simply a diagonal matrix of n ones. So instead of di's, we would have only ones. One important thing here to note is that the definition is a bit ambiguous, the definition of the identity matrix, since it does not specify the dimension of ones, right? So this is sometimes understood from the context, and it has to be done in a way so that the matrix multiplication is possible. Yeah, so if A is in R n times n, then I also has to be such a matrix. So it has to just agree with the definition of the matrix multiplication.
Nice, Prism. There were some questions regarding matrix and matrix multiplications. Maybe could you perhaps give some examples of maybe a 2x2 matrix?
Yeah.
So that people can maybe follow. It's like, how does it work?
Have more space. Maybe here.
Thank you.
Welcome. All right, so let's say we would have a matrix A, which is this matrix 2, 3, 1, 4, 5, 6. So this is a 2x3 matrix. And then we would need the other matrix to have the first dimension 3 for sure. And the other dimension is actually free to choose, but let's choose it to be 2. So 0, 1, 2, 1, 1, 2. then their product. This one is the matrix B. All right, so first of all, we have the first matrix A, which is a 2 by 3 matrix, and the matrix B, which is a 3 by 2 matrix. So the second dimension of A agrees with the first dimension of B, and we know that the dimensions of the product matrix will be the first dimension of A times the second dimension of B. So it will simply be A 2 by 2 matrix. All right, so then how it works. We have first entry here, second entry here, third here, fourth here. Let's find each of them separately. So the first entry would be first row times first column. 2 times 0, 0, plus 1 times 2, 2, plus 5 times 1, 5. So the first entry is just 7. The second entry is the first row of A times the second column of B. So this is 2 times 1 equals 2, plus 1 times 1 equals 1, plus 5 times 2 equals 10. This is 13. The third entry is the second row of A times the first column of B. This is 3 times 0, 0, plus 4 times 2, 8, plus 6 times 1, 6. This is 14. And the fourth entry is the second row of A times the second column of B. So this would be 3 times 1, 3, plus 4 times 1, 4, plus 6 times 2, 12. So this is simply 19. So yeah, if we are to write the matrix C, this would simply now be 7, 13, 14, 19. So this would be the product matrix. Okay, I think this is clear, but I think we will have to deal with matrix multiplication even at some later point. So if you still did not understand this, I hope you will still be able to continue with the materials. All right, another important concept is the concept of the transpose, which we have actually been denoting so far very often, but we didn't give a clear definition for it. So the transpose of a matrix A in Rn times n is simply a matrix n times m, where the ijth entry of the matrix transpose A is simply iji. I can explain this with an example. If A were to be 2, 1, 3, 2, 1, 1, then the A transport is the first row of A becomes the first column, and the second row of A becomes the second column. And some properties of the transpose is that the transpose of A is simply the original matrix. So if you were to retranspose this matrix, you actually simply get back the original matrix. Another property is that the transpose of the product of matrices A and B is simply the product of the transpose of B times the transpose of A. And the third property is that the transpose of the product A and B, of the sum of A and B, is simply the sum of the transpose A and transpose B. All right. Then we also need symmetric matrices. So we say that a matrix R in n times n is symmetric if A equals to its transpose. And we say that it is antisymmetric if A equals the negative of its transpose. So some properties that you can really easily check is that the summation of A and transpose A is symmetric on its own, and the subtraction of A transpose from A is actually antisymmetric. And A is simply the summation of 1/2 the sum of A plus A transpose plus 1/2 of A minus A transpose. And we actually, this set of symmetric matrices of size n, so containing n by n entries where A equals A transpose, will be used very often. So we simply denote this by this calligraphic S to the power of n. So yeah. The second property here, it just means that, so this property here, so this property here, it just means that any matrix A can actually be expressed as a sum of asymmetric and an antisymmetric matrix, since the first one, as we saw from the first property, is symmetric, and the second one here is antisymmetric. All right. And then we have the definition of the trace. So the trace of a matrix A in Rn times n is simply the summation of its diagonal entries. So if we were to have 1, 2, 0, then the trace of this matrix is simply 1 plus 2 plus 0. This is 3. One thing you have to keep in mind is that the trace is actually only defined for square matrices, or the so-called symmetric matrices. So some properties is that the trace of a matrix A is equal to the trace of the transpose of a matrix A, and if we have two matrices A and B in R n times n, then their trace of the sum of matrices A and B is equal to the sum of the traces of A and the traces of B. And if we have a matrix A in R n times n, and if we have T a scalar in R, then this scalar T actually can get in front of the trace of a matrix A. And if A and B are matrices such that their product is square, then the trace of the product A and B is equal to the trace of the product B and A. And in order to prove this product, we can simply suppose that A is a matrix in Rn times n, and B is a matrix in n times n, so that AB is a matrix in Rn times n and is a square matrix. And we also observe that this other matrix, B times A, is also a matrix in n times n and also a square matrix, so it makes sense to apply the trace operator. We first begin by using the definition of the trace operator here. So this is just the summation of the diagonal elements of the product matrix A and B. And here we apply the definition of the matrix multiplication. On this equation, we actually use the commutativity of scalar multiplication in order to reverse this summation. So we simply take the second summation first and the first summation second, and we also exchange the bji and iaj. And then we simply rearrange this summation, and then by the definition of matrix multiplication, this simply gives the product of matrices B and A. And then this other one, by the definition of the trace, simply gives the trace of the product matrix B times A. And if we have three matrices, A, B, and C, such that the product A, B, C is a square matrix, then we actually have this property that the trace of the matrix ABC is equal to the trace of BCA is equal to the trace of CAB. So the proof for this one would be very similar to what we have over here, but just we have more matrices, one more matrix. All right, another very important definition that is used a lot in data science is the definition of norms. And by definition, a norm is any function f from Rn to R which satisfies these four conditions. The first one is that for all x's in Rn, the f of x is non-negative. The second condition is that f of x is equal to 0 if and only if x is 0. This is so-called the definiteness property. The third condition is that if x is in Rn and t is in R, then the scalar is taken in front but on the absolute value, the so-called homogeneity. And the last one is that for all x's and y's in Rn, then the f of x plus y is less or equal than the sum of f of x and f of y. This is also so-called the triangle inequality. Some examples of norms include the famous LP norm, which is simply the sum I from 1 to n, the absolute value of xi to the power p, and the whole summation squared to the power 1 over p. One specific example of LP norm is the so-called Euclidean L2 norm, which simply measures the length of a vector. Simple example of this would be if we would have a vector x 1, 2, 3, then the L2 norm would simply be 1 squared plus 2 squared plus 3 squared. So yeah, this would simply give the length of this vector in space. So in this case, we would have a three-dimensional vector, and the length of such a vector is square root of 14. Another very famously and widely used norm is the definition of L1 norm. This is actually one of the norms that is highly used, for example, in compressive sensing, or in this recommendation system that we saw from Netflix at the very beginning, because this norm by the definition imposes sparsity. So this is very famous in machine learning, and you here instead just take the sum of the absolute value of the entries of xi. So if x was, let's say, -1, 2, -4, then x1 would simply be -1 plus the absolute value of 2 plus it will simply be 7. And the L infinity norm, it's just defined as the maximum entry of vector x on the absolute value. So in this case, if x was -1, 2, and -4, then the L infinity norm would be, if we denote this entry 0, 1, 2, it would be 2. So the second entry of the vector x contains the maximum value. Norms can also be defined for matrices. So, for example, here we have the so-called Frobenius norm, where we again take the squared root of the summations of the square entries of matrix Aij, which also by definition is simply the square root of the trace of product matrix A transpose times A. All right. Yeah, so then we have one exercise about the norms. We want to show that the length of A times X, where A, I haven't written here what A and X are, but from the context, you should already understand that A is simply a matrix and X is a vector. We want to show that the length of this vector equals the length of A transpose X if A transposed is equal to A transposed A. And the solution to this exercise is really simple. So to show that the length of A of X equals the length of A transpose X, we simply take the L2 norm squared of AX. This, by definition, what we saw here before, is simply the product between the transpose of AX and itself, AX. And then we just apply the property that the transpose of AX is equal to the X transpose A transposed, AX. And then, sorry. Here, it's where we use this equation. And then again, for these two entries, we can simply rewrite them as the transpose of A transpose times X. And the second two terms we keep in the same fashion. And this is again just the definition of the squared norm. All right, so this is a relatively straightforward exercise. And then one very important concept is the definition of linear dependence / independence. So assuming that we have a set of vectors x1 to xn in Rm, we say that they are linearly independent if no vector can be represented as a linear combination of the remaining vectors. And in the other hand, we say that the set of vectors x1 to xn in Rm is linearly dependent if one vector can be represented as a linear combination of the remaining vectors. So in a sense, there exist these coefficients alpha I in R such that we can represent xn as the linear combination of vectors xi. A simple example is if we have these three vectors, x1, which is simply 1, 2, 3. Sorry, this is x2 and this is x3. 4, 1, 5, and x3, 2, -3, and -1. They are linearly dependent because we can see that x3 can be expressed as -2x1 plus x2. So yeah, in this case, alpha 1 is -2 and alpha 2 is simply 1. All right. Then we have the concept of rank. So the rank of a matrix. The column rank of a matrix A in Rm times n is the size of the largest subsets, the size of the largest subset of columns of A that constitute a linearly independent set. On the other hand, the row rank of a matrix A in Rm times n is the size of the largest subset of rows of A that constitute a linearly independent set. So just looking at a matrix either as a matrix of column vectors, of row vectors, then we just find how many of them we can find such that none of them can be expressed as a linear combination of the other ones. And this simply gives us either the column rank or the row rank. And then for any matrix A in Rm times n, the column rank of A equals simply the row rank of A, or the so-called simply rank of A.
So person, there was a questions about how can we quickly find out whether or not a matrix is has linear independent rows and columns?
Yeah, so for that, you can I think in SciPy, for example, using Python, you can simply input the vectors that you want to check if they are linearly dependent or independent, and it will automatically do it for you. But like if you want to do it by hand, there is no algorithmic way to find it. As far as I know, you would simply look if you could find some sort of relation between of them. But yeah, I would say the best way to do this is using a machine. So yeah. Yes, actually, I could say more about linear dependence or independence is that they are also used when one wants to do a dimensionality reduction, because when you have one vector which is expressed as the sum of other two vectors, then these three vectors, actually x1, x2, and x3, are in 3 dimensions. But actually, since we can express them as a linear combination, they actually rely on a 2-dimensional space in this 3D space. So if we were to have a 3-dimensional space, and let's say this would be x1, this would be x2, x3 would be something like here. So they, in a sense, all lie within this 2-dimensional subspace in the 3-dimensional original space. And in 2 dimensions, this is easier to visualize, because in 2 dimensions, in 2 dimensions, we would have, let's say this would be x1, and this would be x2. So x1 would be just some factor alpha times x2. So you would have them in 2 dimensions, but actually they would be the same vector, just one would be a multiple of the other vector. So yeah, we sort of, in 1 dimension, we get stuck in one vector. So in 2 dimensions, we would have 1 dimension less. And in 3 dimensions, we would stuck in a 2-dimensional space. All right, so then we had the definition of the rank of a matrix. So yeah, this is by just checking what is the maximum amount of either rows or columns of a matrix, such that they are not linearly dependent. And some properties of the rank of a matrix is that for a matrix A in R m times n, then the rank of a matrix A is less or equal than the minimum of m times of the minimum between m and n. So this makes sense actually, because if your matrix contains only m rows and n columns, then the rank has to be smaller than the minimum of rows and columns. We say that the matrix is a full rank if the rank of A equals the minimum between the dimensions m and n. Another property is that if A is in R m times n, then the rank of A equals the rank of the transpose matrix of A. And if we have two matrices, A in R m times n and B in R n times B, then the rank of the product matrix A times B is less or equal than the minimum between the rank of A and rank of B. And if we have two matrices A and B in R m times n, then the rank of A plus B is less or equal than the rank of A plus rank of B. All right. Then we have the definition of the inverse. This is also used a lot. For example, when we had this example at the very beginning with the system of two linear equations that we wanted to solve, then we express this system of linear equations in terms of matrices, and in order to find the solution of it, we actually need the definition of the inverse of a matrix. And by definition, the inverse of A in R n times n is a matrix A to the power -1, which is the unique matrix defined in this way. Sort of, if we multiply A from the left by the inverse, this would simply give us the identity matrix. And this is the same as if we were to multiply the matrix A on the right by matrix inverse A. We have to note that not all the matrices have inverses. For example, non-square matrices do not have inverses by definition. We also say that A is an invertible or non-singular matrix if the inverse of A exists, and non-invertible or singular otherwise, so if the inverse does not exist. Another property is that A has an inverse of A if A is a full rank. Some properties for two matrices A, B, and R n times n is that the inverse of the inverse of A gives us back the matrix A. The inverse of the product A times B gives us the product of the inverses between B and A. And the transpose of the inverse A just gives us the inverse of the transpose matrix, which is also denoted usually by the A to the power or A to the minus transpose. Okay, so I already wrote here when we use the inverse. So if we have the system of equations Ax equals to B, where A is a matrix in R n times n, and X and B are in Rn, and then if A is non-singular or invertible, then X is equal to the product between inverse A times B. So what if the A is not a square matrix, then this does not make sense. But actually, we will also later see that even some square matrices don't have inverses. So it is it's a necessary condition, but it's not sufficient. So we will see that there are many alternative, sufficient, and necessary conditions in addition to full rank, which we already saw on the fourth property on this slide, in order for a matrix to have inverse. All right, so then we have a definition of the determinant of a matrix. The determinant of matrix A in R n times n, denoted by this. expression, or the determinant of A, is simply a function from R n times n to R. So it gives us simply an element in R. And by definition, this notation is a matrix which results from the deleting the ith row and the jth column from A. The definition for such a matrix is necessary for us to give the recursive formula for the definition of the determinant, which is simply given by the sum I from 1 to n minus I to the I plus j aij times this matrix. And this can also be written in terms of columns. So you can either sum in terms of rows or in terms of columns. By definition, the determinant of a matrix which has only one element in R is simply that element. So this is the first one. And then by definition, again, the determinant of a 2 by 2 matrix is simply A11 times A22 minus A12 times A21. And we continue so on. So if we have a 3 by 3 matrix containing these elements, then the determinant of such a matrix, I think here we are going by the definition of the first row. So we have the first element of the first row, A11, and then we take the matrix which results by deleting the ith row and the jth column, which is first row and first column. So we then have A22, A23, A32, A33. And then we have the minus A12. Again, we delete the first row and the second column, so we are left with A21, A23, A31, A33. And then we delete again the first row and the third column, so we are left with A21, A22, A31, and A32. And then again, for these three matrices over here, we simply use the definition for a 2 by 2 matrix.
Mr. President, would it be possible to give an example of the determinant and also the inverse as well? Thank you.
Okay, so let's say we have a matrix. All right, so let's say we have this 3 by 3 matrix, and let's say I don't want to follow this definition which I have over here, but I would like to go by the definition of the first column. So by definition, we would take the first element of the first column, 2, and then the other 2 by 2 matrix would be by removing the first row and the first column. So we are left with 0, 0, 1, 3. Then we would have minus the second element of the first column, 1. We remove the first column and the second row. So we are left with 3, 4, 1, 3. And then we take the third element, 2. We remove the third column, the first column and the third row. We're left with 3, 4, 0, 0. So this is then simply, I would continue here. This is simply 2, 0 times 3, 0 minus 1 times 0, 0, minus 1, 3 times 3, 9, minus 4, plus 2, 3 times 0, 0, minus 0. So this is, I mean, these terms cancel because we have 0, and then we would have minus 5. Right, so yeah, this is how we would calculate the determinant of the 3 by 3 matrix. And you can go by any, you can start by any row or column that you want. You simply use this definition over here. And for the inverse, I think we will have some examples in the programming part, so I would leave it for that, because as far as I see here, we still haven't given the closed form solution for the inverse. All right. Yeah, so then some properties of the determinant is that the determinant of the identity matrix is simply 1. If we would have a row of matrix A multiplied by a scalar T, then we can just take this scalar T in front and calculate the determinant of A. And if we have a matrix A star, where we have exchanged the first row with the second row, then this is just the negative of the determinant of A. So yeah, by exchanging two rows, then the determinant of the new matrix is the negative determinant of A. In order to give a more intuitive definition of the determinant, the way to understand it better is that it just describes how much a sample area changes in scale with a linear transformation. So in this case, let's say we have scaled the vector I by 3 and the vector j by 2. Then the area that these two vectors actually cover has scaled from 1 to 6. So the determinant in this case would be 6. All right, and so yeah, when we increase the area by a factor of 6, this factor is known as the determinant. So yeah, determinants describe how much a sampled area in a vector space changes in scale with linear transformation. And this actually can provide us very helpful information about the transformation itself. Some other properties is that the determinant of a matrix A equals the determinant of transpose of A. If we have two matrices A and B in Rn times n, then the determinant of the product A times B equals the product of the determinants of A and determinant of B. And if we have a matrix in Rn times n, then the determinant is 0 if and only if A is singular or non-invertible. So it means that it does not have full rank, which means that its columns are linearly dependent. So yeah, if we were to have it in this case, then this would be the vector I. So the vector j would be just an extension of it, so that they don't have any area that they are generating, even though we are scaling them. They have no area which they are generating between of them. So in that case, the determinant would be 0. And if A is a matrix in Rn times n, and if A is non-singular, then the determinant of the inverse just equals the fraction 1 over the determinant of A. So in this case, it's the determinant 0. We have it already in this example, in the slide. Another property of determinant is that shears and rotations do not affect the determinant. So before we had which they had a surface of 1, and if we were to scale, then the area that again they would span would have the same surface, so it would be 1. And linearly dependent transformation result in a determinant 0. So in 2D, as we saw, this would just compress into 1 dimension, and in 3D space, this would compress into 2 dimensions. One very simple exercise that we could do with determinants is that if we have a matrix A, which has a determinant of 1/2, Then we want to find the determinant of the matrix 2 times A, the determinant of the negative matrix A, the determinant of square matrix, and the determinant of the inverse. So for the first one, we just use the definition of the determinant, and we take, so this 2 is actually multiplying all the columns of the matrix A. So by using this property that we had, so yeah, using this second property, we would take 2n times. So multiplying it n times would give us 2 to the power n. And then the determinant of A is 1/2. So this is simply 2 to the power n minus 1. The determinant of negative A is simply taking minus n to the power n and the determinant of A. The determinant of squared matrix A is simply the product between the determinants of A. This is 1/4. And the determinant of the inverse is 1 over the determinant of A, and this is simply 2. All right. Okay, I also had another example here, how to compute the determinant of these matrices. So the first exercise is actually where we combine both the matrix multiplication and find the determinant. So we have a column vector 1, 4, 2 and a row vector 2, minus 1, 2. So first of all, we use the definition of the matrix product. This would just result in a 3 by 3 matrix. And then we reapply here the definition of the determinants. And I did this again here, going by the first row of this matrix. So we have in the first entry 2, the second entry minus 1, but we have minus 1 from the definition, so it becomes a plus. And we have the third one 2, which is also here. Then we have the determinant of U. As we see from the definition of U, this is a so-called upper diagonal matrix because the lower part of this matrix contains all zeros. So how we compute the determinant in this case is we just multiply the products of the diagonal elements. And this is also equal to the determinant of the transpose U. And for the inverse, we use the property that the inverse, I forgot again. This is the fraction between 1 and the determinant of U. So we just use that the determinant of U is 16. So this is 1/16. All right. Yeah, before going to eigenvalues and eigenvectors, I would like to go to the coding part. Actually. All right, so let's continue a bit with the programming part. So for those of you that are new to Python, I would suggest that you go through these 2 links. There are a lot of tutorials online. You can just pick whichever you want. If you never worked with NumPy or Algebra before, then yeah, you have these links to go through. I want to note here that this is not an introductory course to Python or anything like that. It assumes a bit of knowledge in Python, but yeah, I will just want to demonstrate some of the results that we saw from the lecture. All right, so first of all,
Hi, Severson. I'm sorry, could you share the collab link in the meeting? There's a share button on near the top, near the settings. If you change restricted to everyone, then there should be a link. Thank you.
All right, so yeah, first we just start by defining a vector using a list, sorry. Then we want to define a vector v using numpy. For that, we can just import the library numpy and then just do an array. Let's say 3 times 2, so we can print this again. We can also define a 3-dimensional vector. Or we can define a 4-dimensional vector. All right. So then we can do operations with vectors. For example, we can add them. And the way to do this we simply at first define the vectors v and w. And in NumPy, it's actually very straightforward how we add them. So we just do v plus w, and this gives us 5 and 1, which is the product of these two vectors. What we saw again from the lecture is that we can scale a vector. And in this case, the scaled vector v would be we can print this vector. So we have to note that scaling a vector does not actually change the direction, but only the magnitude. And when we multiply by a negative number, then the direction is flipped. Then we have matrix vector multiplication. So when we declare a matrix A by this matrix 3, 0, 0, 2, and a vector x 1, 1, then their product would simply be, we are again here using NumPy. So yeah, this would just give us the product between any matrix A and any vector x, assuming that their dimensions agree. We can do matrix-matrix multiplication, and the way to do that is this again would give us the product between a matrix A and B. Then we have the definition of the determinant and how we calculate the determinant of a matrix A. For this, we need linear algebra package from the library NumPy, and we import the determinant. And the way to find the determinant is just by applying this operator on A. And yeah, as we saw from the lecture, by definition, this is just 3 times 2 minus 0 times 0, so this equals 6. And then we, as I said, we will also compute the inverse of a matrix, but now we will use the library SumPy. So the idea of this notebook is just to introduce you to a lot of existing libraries for introducing to a lot of libraries for doing linear algebra that is required for data science. So then we have this matrix 4, 2, 4, 5, 3, 7, 9, 3, 6, and we want to find its inverse. Let's save into a variable called inverse. So this is just a inverse. And then we want to print this. So yeah, this is the inverse. Actually, by definition, this is just 1 over the determinant of A times the matrix A, but the SciPy package does this automatically for us. And as I said, the definition of inverse is very important when we have to solve a system of equations. And we can very easily do this using, again, SciPy. So if we have this matrix 4, 2, 4, 5, 3, 7, 9, 3, 6 again, and we have a matrix B given by 44, 56, and 72, then again, as we saw from the lecture, we want to solve this system of linear equations AX equal to B. And for that, X is actually just computed by multiplying the inverse of matrix A with the matrix B. So in this equation here, we take the A to the right, we multiply from the left by inverse of A, and multiply it with B. So this just gives us the inverse. But
could you also enlarge the screen a little bit so people can see a bit more clearly? Perfect, thank you.
Okay. All right. Not only we can do the finding this or solving the system of linear equations using SciPy, but we can also do this using NumPy actually. And the way to do this, again, we have the same matrices A and B, and X is simply the inverse of A dot B. And then we can print X. So as we see, it's again the same result. It's just that NumPy has a different syntax for showing the matrices. All right, and we did not start with eigendecomposition yet. I think now we could have a break of 10 to 15 minutes, and then we would continue the lecture with the eigendecomposition. And then we could also continue with the rest of the coding, if that works well for you.
So we'll be back in 15 minutes, right, Mr. Person? Okay, perfect. Thank you.
Anywhere you go, you belong. Anywhere you say, anywhere.
Mr. President, are you back yet?
Yes, yes, yes.
That's good. I don't think we can see your camera view.
Okay.
Okay, perfect. Thank you. And also, could you adjust the volume? So next to the mute button, there should be an arrow up there.
Mhm.
If you click on it, there should be an audio settings at the bottom.
Yes.
And when you click on it, you can adjust the output volume. Can you increase it a little bit? Because some people say that they cannot hear very clearly because the volume level is quite low.
I can try with AirPods if that works better. 1 second.
Yes.
Is it any better?
Yeah, better.
Okay, perfect.
Thank you.
All right, so we'll just continue on where we left. So the next topic would be eigenvalues and eigenvectors. All right, so lambda, a complex number, is an eigenvalue by definition. If for a vector x in the space of complex number to the power n, is its corresponding eigenvector of a matrix A in R n times n, if A times x equals lambda times x for x different than 0. So multiplying A by the vector x results in a new vector that points in the same direction as x, but it's scaled by a factor lambda. And what we can do here is that we say lambda and x is an eigenvalue, eigenvector pair of A if lambda times the identity minus A multiplied by x is equal to 0. So this is just a simple deduction from the equation before. So if we take x to the 0, or no, actually. Then we can just factor the x. So this would give us this equation. And this equation has a non-zero solution to x if and only if this matrix lambda times the identity minus the matrix A is singular. And as we saw from before, this means that its determinant is 0. So the determinant of the matrix lambda times I minus identity minus A is equal to 0. And this just results actually in a polynomial in lambda, which is of the order of n. So if we were to express this equation, this would just result in a polynomial whose roots of this so-called characteristic polynomial lambda 1, lambda 2, and lambda n are the so-called eigenvalues of the matrix A. And then the way that we find an eigenvector which corresponds to the eigenvalue lambda I is just by solving this system of linear equations. So we have the eigenvalue lambda I times the identity matrix I minus some matrix A multiplied by the vector x equals to 0. All right, some properties of eigenvalues and eigenvectors is that for any eigenvector x in the space of complex numbers to the power of n and a scalar t, also a complex number, a matrix A multiplied by scalar c times vector x is equal as if we multiply from the left by the scalar c, the matrix A times x. And from the definition, A times x is simply lambda times x. And we can take this lambda in front of the product c times x. So this means that c times x is also an eigenvector. And this is why we actually a lot of times work with unit eigenvectors. The eigenvector associated with lambda is normalized to have length 1. Some other property is that the trace of A is equal to the sum of its eigenvalues. The determinant of A is equal to the product of its eigenvalues. The rank of A equals the number of non-zero eigenvalues of A. And if A is non-singular, then 1 over lambda I is an eigenvalue of the inverse matrix of A with associated eigenvector xi. So mathematically, this is just inverse of A times xi, which is 1 over lambda I times xi. And eigenvalues of the diagonal matrix D are the diagonal entries D1 to Dn. To actually prove this one, we would simply left multiply each side by inverse A and by A, and we would be able to get the equation. All right. Then we have eigen decomposition. So we can actually write the eigenvector equations simultaneously in this way. The multiplication between matrices A and X equals to the multiplication between matrix X and lambda, where the columns of matrix X in R n times n are the eigenvectors of A. And lambda is a diagonal matrix whose entries are the eigenvalues of A. So mathematically, we can simply write this in this way. So the first column, second column, and the nth column are just first eigenvector, second eigenvector, and the nth eigenvector. And the lambda is simply lambda 1 to lambda n. And if eigenvectors of A are linearly independent, then the matrix X is invertible. So as we saw this from before, if it's linearly independent, then we can find the rank, so then it is invertible. And we can write that the matrix A, we can multiply from the right by the inverse of X. So then we just get this so-called eigendecomposition. And we say that a matrix written in such a form is actually called diagonalizable. And for a symmetric matrix A, so we use this notation which we had from before, calligraphic S to the power n, then all the eigenvalues of A are real numbers. Eigenvectors of matrix A are orthogonal. X is on its own orthogonal, which is also sometimes denoted by U. So we can simply write this as U lambda U transposed. So yeah, for sort of symmetric matrices, then we have a simpler way to write this down. All right. So much for the theory. Let's look at with an example. First of all, we want to find the eigenvalues and eigenvectors of matrices A, which is an upper diagonal matrix, and matrix P, which is a matrix that contains only 2's on the right diagonal. We want to find their traces and their determinants. All right, so first of all, to find the determinant of A, this is really straightforward, as we would simply have 3 the determinant would be just 3. And the other 2 would be 0, so we don't even write them. And this is 3, 1 times 0, 0, minus 0 times 2, 0. So this is 0. Actually, we could have also already found this by noting that the determinant of matrix A is just the product of its diagonal elements. It's an upper diagonal matrix, and one element of its diagonal is already 0, so the determinant is 0. The trace is just the sum of its diagonal elements here. So 3 plus 1 is equal to 4. That's the trace. And to find the eigenvalues and eigenvectors of matrix A, we will first start by writing down the characteristic polynomial of the matrix A. So we have the determinant of A minus lambda times the identity matrix I. We subtract from the diagonal elements lambdas. So we have 3 minus lambda, 1 minus lambda, and minus lambda equals to 0. And then by just computing the determinant of this matrix, we would have 3 minus lambda times lambda squared minus lambda equals to 0. So it is easy to see that its eigenvalues are 0, 1, 3, and the corresponding eigenvectors are these ones. Actually, to find these eigenvectors, we simply use this equation. Eigenvalue times the identity minus A times X equal to 0. All right, so yeah, maybe we can do this. Notebook. Okay. I hope you can all see my notebook. So we have 3 minus lambda, lambda squared minus lambda. So what you do, you just factor one lambda, and then you have lambda minus 1 equals 0. And this product is 0 when each of them is 0. So we just see that lambda 1 equals 3, lambda 2 equals 0, and lambda 3 equals 1. All right. So yeah, 0, 1, and 3 are the corresponding eigenvectors. And to find these were the eigenvalues. To find the eigenvectors, we use this equation. Our matrix A is all right. So the way that we find this, let's say the first lambda 1 is 0, then we would have 0 times the identity matrix. In this case, we have a 3 by 3 matrix. So we have 1, 1, 1, 0, 0, 0, 0, 0, minus 3, 4, 2, 1, 0, 2, 0, 0, 0. Times x equals 0. So we would just have minus 3, 4, 2, 0, 1, 2, 0, 0, 0. This cancels. 1 is 2 is 3. Now we just do matrix multiplication. So first we can just do this. All right, so then we do matrix times vector multiplication. So minus 3x1 minus 4x2 minus 2x3 equals 0. For the second one, we would have minus x2 minus 2x3 equals 0. So we have this system of equations where we see that we only have 2 equations and we have 3 unknowns. So we can already start by keeping S3 as a free variable. So then we would have that 3x1 plus 4x2 plus 2x3 equals 0. And we would have x2 plus 2p. We substitute everything on the first equation. and we get 8t. All right, so then x1, x2, x3. Actually, we don't have a unique solution, but we have many solutions. So this is just 2t minus 2t, and this was t. And if we simply take t to be 1, and then one solution of this equation would be x1, x2, x3, 2 minus 2, 1. So for lambda 1 equal 1, eigenvalue corresponding vector is 2 minus 2 and 1. All right, so this is exactly this one over here. In a similar fashion, we would also find the eigenvectors for lambda equal to 2 and for lambda equal to 3, which would be just minus 2, 1, and 0. And 1, 0, 0. All right, so I hope this computation of eigenvalues and eigenvectors is so far a bit clear, but I will go through this once again. And we will also see in the coding part that we can ask Python to do this automatically for us. In a similar fashion, we have the matrix B, which is simply 2, 2, 2, 0, 0, 0, 0, 0, 0. So for the matrix 2, we also calculate the determinant first. We can either use the definition or simply by noting that we have the inverse diagonal, so that it is the negative times the product of its diagonal elements. The trace of B is the sum of the diagonal elements, but as we saw, it's also the sum of its eigenvalues. So as we see from here, we will calculate them in a bit, but its eigenvalues are minus 2, 2, and 2. And if we were actually to add them up, this would simply give us 2, which would also be the trace of B. So yeah, the trace of B is the sum of lambda i's eigenvalues. Again, to find the eigenvalues of the matrix B, we just write down the determinant of the matrix B minus lambda times the identity matrix I equals to 0. We subtract from the diagonal elements of the matrix B lambdas. So we have minus lambda, 2 minus lambda, and minus lambda. We find the determinant of such a matrix. So we have minus lambda, 2 minus lambda times minus lambda minus 4, 2 minus lambda. We then find that the eigenvalues are minus 2, 2, and 2. So yeah, as you can see, two same eigenvalues can lead to two different eigenvectors. And to find the eigenvectors, in this case, I have shown an alternative way to find them. So I didn't do this via solving the system of linear equations, what we did before in this notebook, but I just tried to find a way to express. So this is simply matrix B. This is lambda, and this is x, x. So I tried to find x's which satisfy bx equal to lambda x. And this is simple to do because in this case, matrix P is rather simple. So we can just see that the product between the matrix P and this eigenvector -1, 0, and 1 is the same as if we had only one value, -2, -1, 0, 1. And similarly, for the other two eigenvalues 2 and 2, we could see that some vectors which would satisfy this relation could be 1, 0, 1 and 0, 1, 0. So yeah, the suggested way to find eigenvectors is via solving system of linear equations, but in case you can already see this by simply doing some matrix multiplications on your mind, then you can get this. So there's one question: how can we get -1, 0, 1? Well, you get this -1, 0, and 1 the way we did here. So sort of by solving the system of linear equations. But in this case, I just saw it by actually just quickly checking, because if you multiply this matrix with this vector, you get the same as if you were to multiply this value by this vector. So this side and this side, they both give the value 2, 0, -2. And the same for the other two eigenvectors. All right, so then we have systems of equations and inverse matrices. So as we saw, system of equations are important, for example, when we had to find the eigenvectors corresponding to a certain eigenvalue. Note that they can have multiple solutions or they can have a unique solution. So we would have a unique solution in case the matrix which represent this system of three linear equations would have a full rank. So yeah, basic use of linear algebra is to solve systems of equations of this type, for instance. And ways to solve this would be via solving it manually with algebraic operations to isolate three variables. This is what we did in the notebook. Another way would be to express a problem in terms of matrices, and we could let a computer solve it. So we would just express this system of three linear equations via the matrix A, where we keep only the coefficients for the three dependent variables x, y, and z. With B, we would denote the coefficients after the equation signs of 44, 56, and 72. And for x, we would have the three dependent variables x, y, and z. We could again solve this by hand using the so-called Gauss elimination methods, or we could use the computer to find the inverse matrix A-1, which is what we did in the Google Colab, and as we will see later. All right. So yeah, the best way to do this is always to sort of extract the coefficients into a matrix. A, the values on the right side of coefficients into matrix B, and the unknown variables into a separate matrix X, which you can then use a computer to find the solution. All right, so then we have another exercise using the characteristic polynomial. So the characteristic polynomial was the one that resulted by taking the determinant of the matrix minus lambda times the identity matrix. So using this characteristic polynomial, we want to find the relationship between trace, determinants, and eigenvalues of any square matrix. All right, so for that, we can just first let the matrix A denote this square matrix n by n, and we denote its eigenvalues by lambda 1 to lambda n. So the characteristic polynomial of this matrix would simply be by taking the determinant of lambda I minus the matrix I, and this would simply result in a polynomial of degree n minus 1 on the lambda, and we would have sorry, on the degree, I think we're missing one degree. It's on the degree n of lambda, and then we would have coefficients Cn minus 1, C1 to C0. All right. So then we know that the eigenvalues of a matrix A are zeros of this characteristic polynomial. So we could write the characteristic polynomial as lambda minus lambda 1, lambda minus lambda 2 times many products lambda minus lambda n. So what we're going to do in this exercise, we're going to play with these two coefficients, Cn minus 1 and C0. So first of all, we can express the determinant of a product of eigenvalues, as we saw here. And then, if we just consider this for lambda equal to 0, then we substitute on this equation here all the lambdas to be 0. So this would just give us the product of eigenvalues and minus n to the power n. But on the other hand, from the definition of the characteristic polynomial, we would also have that this is simply the determinant of lambda is now 0, identity matrix minus matrix A. So this cancels out. So we just have the determinant of minus matrix A. And as we saw before, this is just minus 1 to the power n times the determinant of matrix A. So now we actually have two ways to express this coefficient C0. One is as product of lambda 1 to lambda n multiplied by minus 1 to the power n. And the other one is minus 1 to the power n times the determinant of A. So this just means that the determinant of A actually equals the product of the eigenvalues. So this we already had in the exercise. Yeah. So the determinant here, the determinant of matrix B was minus 8, and the eigenvalues were minus 2, 2, and 2. The product is minus 8, so the product of eigenvalues equals the determinant of a matrix A. So first we found the relationship between the determinant of eigenvalues. What about the relationship between the trace and the eigenvalues? We already saw this here as well, that the trace of a matrix equals the sum of its eigenvalues. Can we actually prove this? All right, and in order to prove this, we can express trace as sum of eigenvalues. So we first expand the characteristic polynomial, which is lambda minus lambda 1 product lambda minus lambda n, to get now the term to lambda n minus 1. So now we're playing with this term to find a relationship between the trace of a matrix and its eigenvalues. Before we played with the coefficients which we got for lambda equal to 0. All right, so how we can actually find this term next to lambda to the power n minus 1? So first of all, we expand this expression, which is just the product lambda minus lambda 1, lambda minus lambda n, to get the lambda minus 1 term. And this term would actually just be a product of minus lambda 1, lambda n minus 1, minus 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 lambda, lambda n to the minus 1. Put that here an n. I did not write how we do this, but you can really just see this very easily by taking, let's say, 2. So you would have minus lambda 1 lambda minus lambda 2 lambda and 2 plus lambda squared. But in this case, we want the coefficient here. We don't care about these coefficients. So the coefficients in front of lambdas would just be minus lambda 1 minus lambda 2 lambda, which we can just express as minus lambda 1 plus lambda 2 times lambda. So this is the same as here, but now we have a more general expression when we have not only lambda minus lambda 1 product lambda minus lambda 2, but we have lambda minus lambda 1, lambda minus lambda n. So we have this n times. But just to get the idea, you would still get the same term in front of the coefficients of lambda to the power n minus 1. So this coefficient Cn minus 1 from the previous slide is simply the sum of the eigenvalues. Another way we can write or we can find the coefficients in front of lambda to the power n minus 1 is by simply expanding the polynomial, the determinant of the polynomial lambda times identity minus the matrix A. So we simply subtract from the lambdas the diagonal elements of the matrix A, and we want to find the determinant of this matrix. Again, here we could see that the characteristic polynomial would be a product of lambda minus a11, lambda minus a and n, plus some polynomial of lambda, which has degree at most n minus 2, but which will not have L to the power n minus 1 term. Well, you can see this very easily. So you would just start by using the definition of the determinant. Let's say starting from this element, and then would be this term, lambda minus a11, times the determinant of this other matrix. But note that in this matrix, we only have lambda to the power n minus 2 terms now, because we have removed one way here and one way here. And when they are multiplied by one more lambda, so this would be the only polynomial that could have a lambda to the power n minus 1 term. So since this would be the only polynomial which would have a lambda to the power n minus 1, then the term in front of lambda to the power n minus 1 should be given simply by this expression. So lambda minus a11, product, lambda minus a and n. And if we were to expand this, in the way we did here, this would simply give us a term of this form. All right, so then here I forgot 3 points. So now we found 2 ways to represent the coefficients in front of lambda to the power n minus 1. This is the first one, and this is the second one. So if we combine both of them, then Cn minus 1 is from the first one here, is minus lambda 1 plus lambda n. I'm sorry that I forgot 3 dots here. But this is also equal to the second way for finding the coefficients in front of lambda to the power n minus 1, which is minus a11 plus ann. But from the definition, we know that this just gives us the trace of the matrix A. So it's the sum of the diagonal elements. So this means that trace of a matrix A equals the sum of its eigenvalues. So these are 2 very important properties that we can use to simplify the calculation of the trace of a matrix and the determinant of a matrix. So the determinant of a matrix is the product of the eigenvalues, and the trace of a matrix is the sum of the eigenvalues. All right, I hope this was clear. And then we have another eigendecomposition exercise. So we wanna diagonalize the unitary matrix 1 over square root of 3, and we have now complex numbers. And we want to reach this equation that we had from the lecture. So in order to find the eigenvalues, we start by doing the determinant of V minus lambda times the identity matrix. So just we would substitute V minus lambda 0, 0, 0, lambda 0, 0, 0, lambda. We would find the determinant of this matrix and set it to 0. And I've already done these computations for you, so this would just result in expressions of this form. And if we simplify, these would cancel. And here you would just need to do some multiplication. And we would result in lambda square equal 1. So this would just mean that the eigenvalues would be 1 and minus 1. I think one thing I forgot to mention is that, all right, so one thing that I forgot to mention is that eigenvectors at the end of the day are just vectors who have the same direction as if we were to unify them, to make them of length 1. So this relationship actually is true, and it holds for either x normal eigenvector, but it holds true for x if we are to make it unitary. So if its length become 1. So yeah, regardless of whether we use a regular eigenvector or if we use the unitary eigenvector, then we have that the product between b and x equals the product of lambda and x. All right. So yeah, back to this exercise now. We find that the eigenvalues are 1 and minus 1. So by the way that we defined the matrix lambda, it was just by stacking on the diagonal the eigenvalues of a matrix. And in this case, we have a 2 by 2 matrix whose eigenvalues are 1 and -1. So we can just stack the eigenvalues to get the matrix lambda. After we have found the eigenvalues, we can find the corresponding eigenvectors. And to find them, we would simply use the fact that should give us 0. We would use the fact that V minus lambda times the identity matrix multiplied by the vector x is equal 0. So we would just substitute lambda 1 equal 1 and lambda 2 equal -1. And we would solve this equation to get that the first eigenvector is this one and the second eigenvector is this one. We also saw that the matrix U in this decomposition, U is actually unitary eigenvectors of matrix V. So we normalize these vectors to get the matrix U. And the way you normalize a vector is by just dividing. Let's say we have a vector A equal x1 and x2. Then unitary A is just A over the length of A. So you divide by the length of that vector, and the length of that vector is simply given by x1 square root x1 squared plus x2 squared. All right. So here I would like you to take as a homework. It is rather straightforward. You would just need to use to open up using the definition of matrix multiplication. So if you have a 3 by 3 upper triangular matrix with interest Tij, so you would have a 3 by 3 T matrix T11, T12, T13, T33, T22, T23. So actually, what we need to show is that if then T is diagonal. So yeah, like the product of the transpose of T with T equals the product of T with the transpose of T, then this just means that T would actually need to be diagonal. So all these entries T12, T13, and T23 would need to be 0. All right, so another very important topic in data science is a singular value decomposition, which is simply a generalization of the eigen decomposition to matrices n times n. So we would have A equals U lambda V transposed, and U is simply an m by m unitary matrix whose columns are the left singular vectors, so-called by definition. We will see later how we find these left singular vectors how we find singular values and write singular vectors. Lambda is an m by n rectangular matrix whose values sigma i's are singular values, and V is an m by n unitary matrix whose column vectors are right singular vectors. So you would just have something like this. So this would be U, this would be sigma, this would be sigma transpose. You have to note that these dimensions all have to make sense. So this would be m times n. So n. This is m times n. So the second dimension of U agrees with the first dimension of lambda. And this, on the other hand, is an n by n matrix. So yeah, also the second dimension of lambda would agree with the first dimension of V, so that this product between all these matrices makes sense. And as I said, it could happen that we would have lambda 1, lambda 2, lambda n, and we would still have entries here. On the matrix U, the column vectors would be just the left singular vectors resulting from finding them from the matrix A. And the V would have columns who are right singular vectors. So we have V transposed, so then we would have, we transpose them, so they would be rows. So this would be the right singular vectors of the matrix A. One very important property is that the singular values of an m by n matrix are actually equal to the positive square root of non-zero eigenvalues of the n by n matrix AT, A transposed A, or also A transposed. So what we would do to find the singular value decomposition of a matrix A, we would sort of just do eigen decomposition of A transposed A or A transposed to find SVD. And furthermore, to find the eigenvectors of the matrix A transposed, we would to find the columns of the matrix U, we would just find the eigenvectors of the matrix A transposed, and to find the columns of B, we would just find the eigenvectors of A transposed A. All right, so we can start with a simple example where we want to find the SVD of this matrix 1, 4, 2, 8. So we want to find the singular values and singular vectors of this matrix. First of all, we begin by finding the product matrix A transposed A. We simply transpose first the matrix A, and then we apply the techniques to do matrix multiplication. We get that the product matrix is just this matrix. Then again, we start doing eigendecomposition of the matrix A transpose A. So this is just the determinant of A transpose A minus lambda times identity matrix equals to 0. We will just substitute 5, 20, 20, 80 minus lambda 1, 0, 0, 1. The determinant equals to 0. So we substitute from the diagonal entries 1 lambda. We find the characteristic polynomial. 5 minus lambda times 8 minus lambda minus 400 equal 0. And from this, we find that the eigenvalues are 0 and 85. It's actually simple to find these eigenvalues, because we could just expand this expression. 400 minus 5 lambda minus 80 lambda plus lambda squared minus 400 equals 0. So these would just cancel with each other. So we would have lambda squared minus 85 lambda equals to 0. We can get one lambda in front. This would be lambda minus 85 equal to 0. So this is 0 when both of them are 0. So we would have that the two eigenvalues are 0 and 85. All right, but what we saw here is that these are the singular values of A transposed A. And in order to find the singular values of A, then we would just simply need to take the square root of them. And the way to find the eigenvectors, we would just again do that times the identity. So then we just find x1 and x2. And in this case, they're just going to be 1, 4 and minus 4, 1. All right, so we did this for finding the left singular vectors. And in order to find the right singular vectors, we need to do the eigendecomposition similarly for the matrix A transposed. In a similar fashion, we would write the characteristic polynomial. So first the determinant of A transpose minus lambda times the identity, determinant equals 0. We would open the expression up, find the characteristic polynomial, and we would find that the eigenvalues are 85 and 0. And similarly to here, we would find that the eigenvectors are 1, 2, and minus 2, 1. So we have everything for doing singular value decomposition from the previous slide. So in the matrix U, we just write down the left singular vectors. In the matrix V, we write the right singular vectors. And in the matrix sigma, we write the singular values, which are the square root of 85 and 0. And another thing here, as you see, we have normalized the eigenvectors. So if you still haven't understood how we normalize eigenvectors, for example, having vector 1, 1 and 4, if we want to normalize it, first we find its length. This is just 1 squared plus 1 squared. So yeah, that's why we are then dividing by the square root of 17. So we just divide the vector 1, 4 by its length. So this just gives us 1 over square root of 17, 4 over square root of 17. All right, and for the left singular vectors, we would have the length of this is 5 and the length of this is 5, so we just both divide these vectors by the square root of 5. And this is how we get the left singular vectors and the right singular vectors, and then we're able to write the singular value decomposition. All right, so then we have another exercise. We want to explain how this singular value decomposition U sigma V transposed expresses the matrix A. Note that A is so we want to express this matrix A as a sum of rank 1 matrices, sigma 1, U1, V1 transpose plus sigma R, UR, VR transpose. All right, so for that, we first write what we wrote before, this expression. And then we write this epsilon y to denote the diagonal matrix which contains only on the ith element of the diagonal the singular value sigma I. So A1, for instance, would be 0, no. This would be sigma 1, and everything else is 0. And sigma k would be 0, sigma k, 0, 0, 0. All right, so then, as we see, the sigma on its own was the stack of all the singular values by stacking them diagonally. So then we just write again the expression for A as U sigma V transposed. We substitute for the sigma that it is the sum of these. I mean, we can note that this sigma is actually the sum of these small sigmas. So we just substitute this expression here. And then we just use the definition that we can take this multiplication of U from the left of the epsilon i's, and that we can multiply by V transposed. So with this, I mean, this is very simple if you were to consider a 2x2 matrix. So in a 2x2 matrix, you would just have U so you would have, let's say here, 1, 0, 0, 0, 0, minus 2, 0, 0. And you can actually just write this as so this is why we can have these expression. All right. I hope this was also clear. So yeah, what we did is that we now are able to express the matrix A as a sum of rank 1 matrices, because all of these small matrices epsilon 1 to epsilon n have a rank of 1. Another exercise is that if A changes to 4a. So if we multiply the matrix A by 4, what is the change in the singular value decomposition? We want to know what is the singular value decomposition for A transposed and what is the singular value decomposition for the inverse of A. All right, so the first one is actually really simple. So when we multiply the matrix A by 4, we simply multiply its elements on the matrix containing the eigenvalues by 4. So then the singular values of 4A are simply 4 times that of A. So yeah, you just, if you were to multiply a matrix by 4, then in SVD, its eigenvalues would be 4 times that of the eigenvalues of matrix A. For the transposed matrix, we write the fact that A is U sigma V transposed, and we have to transpose this. All right, so here we first use so for this one, I skipped one. So the second line would actually be this. So yeah, we just use the fact that if we have two matrices, say the product of two matrices, their transpose is the product of the transposed matrices. So this is the property that we're using throughout this part. And then also we are using that the transpose of the transpose matrix is simply the original matrix. So this gives us back the V. And we have this. So that means that the SVD for the A transposed is by just transposing all these matrices. And the inverse of the matrix A, we again write the definition that A is U sigma V transposed. We take the inverse of that. Again, we saw that the inverse is this one. So we just apply this on everything. And actually, here we know that this U and V are unitary matrices. So for them, it is true that UUT transpose is equal to U transpose U is equal to I, which I already wrote here and here. So yeah, for inverse U, we use U transpose, and for inverse V transpose, we use V. So this just means that the SVD of the inverse of a matrix A is simply given by V, the inverse of matrix of the matrix sigma, which contains the eigenvalues, and the transpose of U. So yeah, sigma minus 1 is just this matrix. All right. And if you want to actually make sure that we have found the correct answer for the inverse A, we can just check this. We could substitute the inverse of A, and the A is simply U sigma V transposed. Well, first of all, this gives us the identity matrix because U is unitary. So we're left with this. This again gives us the identity. So we're left with VW VVT. And this is also unitary. So this again gives us the identity. All right, so I hope this was also clear. A very important concept in machine learning is the pseudo inverse. For example, a regression model. So regression is actually one of the basic building blocks of data science. Is whenever you have a vector of many features and you want to express one feature as dependent on the other one. So this is how you would create regression. I'm not going so much into detail into this model. You can read a lot online about regression. But what is interesting about it is that the regression requires a computation of the so-called Moore-Penrose pseudo-inverse, which is given by this dagger. And this is simply the definition of the SVD dagger. And this is given VD dagger U transposed. Note that this dagger is not transposed. But the definition for the dagger is given here. So the definition of dagger is by taking the inverse of the singular values as soon as we have found them under singular value decomposition. All right. So we have another exercise on pseudo inverse. We want to find the SVD and the pseudo inverse of this matrix A, which is simply a vector matrix. We also have a matrix B, which is a 2x3 matrix, and the matrix C, which is a squared matrix. Again, so we just repeat the procedure. We first do matrix multiplication to find A transposed A. So here, actually, we have the outer product, which there was a question before. What does this mean? Yes, so this is just, it's like a cross. So it's not really a plus, actually, it's more like a cross. And it's used to define the dagger, so-called. So yeah, if you have, let's say, lambda 3 minus 4, 0, 0, and then 1/3. Right. So yeah, it's not a plus, but a plus. All right, so back to the exercise. We first calculate the outer product between the these two vectors, which is simply this matrix containing all ones. And we also compute the A transpose, which would be one. All right, so as soon as we have found these two, then we just find the eigenvalues and eigenvectors of these two matrices. So we just begin. The determinant of A transpose A minus lambda times the identity equals 0. We substitute from the diagonal elements lambda, and all the rest is 0. we find the determinant of this matrix. So this will just give us a polynomial. And then we find the 4 eigenvalues. So for A transpose, I think is simpler to do it because we have just one element. So we would have 4 minus lambda times 1. The determinant of a matrix containing only one element is simply that element. So 4 minus lambda equals 0. So this would simply give us one of the eigenvalues, which is 4. Again, to compute the corresponding eigenvectors, we would just do a transpose minus lambda I x equals 0. And then we would solve this system of linear equations. And in a similar fashion, we would find a transpose I x equals to 0. So again, for the sigma, we just take the square diagonal matrix by taking the square root of sigma i's. V would just contain the left singular vector, U the right singular vectors, and V the U the left singular vectors, and V the right singular vectors. All right. But I think I have done a mistake here because this should be 1/4. Oh no, it's actually correct. Sorry. Yeah, I hope you know why it is correct. Well, again, we have this vector 1, 1, 1, 1, and its length is the square root . So this is the square root of 4. This would give us 2. So we just substitute 2 from each of the elements of this vector. Similarly, the length of the second vector is square root minus 1 squared plus 1 squared is square root of 2. This is also square root of 2, and this is also the square root of 2. So then we just write for B unitary vectors. All right. And then for the pseudo-inverse, we just use the definition. A dagger is V sigma dagger U transpose. Sigma dagger is 1 over the sigma values. And for B, we just substitute the matrix that we had before. And for U, we also substitute the matrix that we had before. All right, so now we need to do the same for a matrix, which is a 3×2 matrix. In the same way, we find that BT transpose B is this matrix. Again, we do determinant of B transpose B minus lambda times the identity equals 0. So this means that we just subtract from each diagonal element 1 lambda, 0, 1 minus lambda, 0, 0, 0, 0. And the determinant of this one is actually straightforward. If we start from this element, then we remove this and we remove this. We have the determinant of matrix 1 minus lambda, 0, 0, 0 equals to 0. Minus 1 minus lambda. This cancels 0. Mistake. No, actually, there is no mistake. Equals to 0. So this means that 1 lambda is 1. All right, and then we would similarly find that the matrix B transposed is this matrix, and we would do again the same steps as for B transposed B. And we find that the eigenvalues are, again, we have two same eigenvalues, 1, 1, and 0. Again, the corresponding eigenvectors are actually the unitary eigenvectors in 3D. So again, we could just deduce this simply by noting this expression. So we had lambda all right, and the way to find this, we could do this. All right. All right, so then we just substitute everything on the matrix sigma. So the two eigenvalues, 1 and 1. In the V, we substitute the three eigenvectors, and U also the two eigenvectors. And the beta dagger is just given by V sigma dagger U transposed. So we substitute everything in, and we find that the B dagger matrix is given by this matrix 0, 1, 1, 0, and 0, 0. In a similar way, you can take this as a homework. You just do the same for the squared matrix C. So C is a 2 by 2 matrix. You first find the product C transpose C and C transposed, which then we find the eigenvalues and eigenvectors. We set the determinant of the C transpose C minus lambda times the identity to 0. We find the eigenvalues 2 and 0. And similarly, we find the eigenvectors by solving these systems of linear equations. Similarly, we find right singular vectors by solving C transpose minus lambda I times the identity times x equal to 0. So we find the left singular vectors and the right singular vectors. We normalize them. These are already normalized. So we have 1, 0 and 0, 1. So their length is 1 squared plus 0 squared. So they're already normalized. We just need to normalize these ones. And we take the square root of 2, which is the square root of the singular value of C transpose C, and find the dagger of C. We just apply the definition and we just substitute the right singular vectors and the inverse of the sigma i's and the left singular vectors here, and we get this matrix as a result. All right, so this is all for the theoretical part. We still have a lot of coding to do in the practical part, but yeah, thank you very much so far for the lecture part. If you want the slides, then you can find them under my website. And yeah, now we can continue with the coding. Right. So we left at we found the determinants before, we found the inverse of the matrix. We did solving a system of linear equations using SumPy and NumPy. And then we have eigendecomposition. All right. So for eigendecomposition in NumPy, we have to import this diag module. And from NumPy.linear algebra, we have to import eigenvalue and inverse. So these are two modules which allow to find the eigenvalues and the inverse of a matrix. So we are given this matrix 1, 2, 4, 5. Maybe I can zoom in a little bit. And again, we want to find the eigenvalues and eigenvectors of this matrix A. And this is actually really straightforward. We just use the eig command, and this will find for us the eigenvalues and eigenvectors. All right, so yeah, we have these eigenvalues, these eigenvectors. Now we want to decompose and recompose the matrix in NumPy. So from the lecture, we saw that A is equal to this x times lambda times the inverse of x. So again, we have the same A. We find the eigendecomposition using this command eig. We find the eigenvalues and the eigenvectors, and we want to find then the matrix X, which was just the matrix containing the left singular vectors and lambda X inverse and the lambda matrices. To do this, we first set the matrix X to be equal to the matrix of eigenvectors. We set the X inverse to be the inverse of X, and the lambda matrix is.
Could you zoom in the screen again as before?
I have it zoomed on my computer. Is it not zoomed for you?
Okay, perfect. Thank you.
All right, and in the lambda, we just stack diagonally at the eigenvalues. All right. And then the next step is to recompute a matrix B and see if this is the same as what we get from the eigendecomposition. So we just do x multiplied by lambda multiplied by its inverse, and then we print the matrix B. And we get the same matrix as the one we started with. So 1, 2, and 4, 5, which we have in the beginning. All right, so the next task that we have is to do dimensionality reduction. What does this mean? Is that what we saw from the lectures, sometimes even though the data might be staying in some three-dimensional space, actually it is in 3D, but they are lying in some 2D subspace of that bigger space. So then in that space, it makes sense that we can remove one dimension. And the way that we do is by doing dimensionality reduction. We see on which direction, on which dimension the variance is the slowest, the smallest, and we can remove that direction and we don't work with that anymore. And dimensionality is very helpful because in that way, for example, we can save a lot of storage. So this is very useful in machine learning applications where one usually works with huge amounts of data, like data can contain thousands of dimensions, but usually what we notice in practice is that the data is actually lying on some small dimensional subspace. So first of all, we want to calculate the covariance matrix. We want to calculate eigenvalues and eigenvectors of sigma. Then we want to plot the original data x and the eigenvectors to a single diagram, and we will observe that the smallest eigenvalue corresponds to direction where the variance is the smallest. And we will then remove this eigenvector, and the new eigenvector will be the basis for the new subspace. And then we will transform all the vectors in X in this new subspace by expressing all vectors in X in this new basis. All right, so first we have this data. So this data contains some 10 to 20 elements, where each element is a two-dimensional array. First of all, we want to calculate the covariance matrix of this input data. So we're given the matrix X, and we want to return matrix D by D, which just gives us the covariance matrix. And we can simply do this by using the np.cov command. Then the next task is to find eigenvalues and eigenvectors of the matrix sigma. So for that, we just do, let's say, L will contain the eigenvalues of matrix S, and U will contain the eigenvectors of matrix S. We use the eigendecomposition given by the numpy, and we simply return U transposed. So in this way, we get the eigendecomposition. All right, the next step is to plot the original data X and the eigenvectors to a single diagram. So actually here I have more or less given all the code for it. The code that is missing is just to calculate the covariance matrix and the eigenvector and eigenvalues of sigma of the covariance matrix. But we can already use the functions that we defined before. So the first function is get covariance. Matrix X. We use the function get sigma, which we defined to find the eigenvector position of a matrix sigma. Yes, so now here, as we see, we have depicted in blue all the data points. And as we see, they more or less, they don't lie in a straight line, but actually they are grouped in this way that's in this direction, the variance is higher than in this direction. So what we observe, what do we observe from this plot, and which eigenvector correspond to the smallest eigenvalue? We notice that the eigenvector in the direction where the variance is the smallest corresponds to the eigenvector with the smallest eigenvalue, so the green eigenvector. And the eigenvalue in this case is this one, 0.375. And instead, in the direction of the red eigenvector, the variance is the largest and it corresponds to the largest eigenvalue. So the value in this case would be 5.625. So yeah, we can then transform the data. As I said, we can remove this direction where the variance is the smallest, and we can just project, in a sense, the whole data in the direction where the variance is the largest. All right, so we have to determine the smallest eigenvalue and remove the corresponding eigenvector, and the remaining eigenvector, which is the eigenvector with the largest eigenvalue, will be the basis for the new subspace. And then we want to transform all vectors in X in this new subspace by expressing all vectors in X in this new basis. All right. So we have this function transform, which transforms the data in the new subspace, which is spanned by the eigenvector corresponding to the largest eigenvalue. So we can save this variable minimum in this which has the smallest eigenvalue. Then we delete from the eigenvectors the eigenvector which correspond to the smallest eigenvalue. And we return the dot product between our data X and this new space of eigenvectors. So then this would be the transform data. So we have the same amount of data points that we had from the beginning. However, we just now have one dimension instead of two dimensions, because we have removed the one with the smallest variance. And the next task is to do singular value decomposition. So we are given a matrix M below, which contains it's 3x2 matrix, and we want to find its singular value decomposition, and we want to reduce it to one dimension. And the way that we do this is by just, as we saw before, we remove the singular values which are corresponding to the smaller singular values. All right. So yeah, we first do singular value decomposition by using the NumPy linear algebra SVD command. We find the minimum which contains the smallest eigenvalue. We delete that from the, we delete the eigenvector corresponding to this minimum eigenvalue. We also delete this from the matrix sigma, and also from the matrix V. But note that now the matrix V is transposed, so we take the first dimension. All right, so then as soon as we have found the smallest eigenvalues, we stack them again into a diagonal matrix containing only the smallest eigenvalues. And then we need to return the dot product between this matrix and our data matrix, which in this case is M. And then if we want to print this new matrix of only one dimension, we would have that it only has 3 entries. Okay. Then we have the task of so-called K nearest neighbor classification. This is also another very important topic in data science. It's one of the basic ones, actually. So when you are given some data points and you want to classify them according to some metric, then what you do, you just compare all your data points to the K closest neighbors, and you look what is the label of these K nearest neighbors, and then you sort of average over them, and you set your label of your image, for example, to be the average of your nearest neighbors. And which elements from the lecture we will use in this exercise is mostly the distance matrix. So the norms, we want to find the distance from one point to all the other neighboring points. The data set which we will use for this exercise is the iris data set. But first, if you are not so familiar with the nearest neighbor classifier, you can read more here. Some of the functions in this notebook are incomplete. We will work with them now. And yeah, so we have in the beginning of every function a docstring. So we have the format of the input and the output, and we want to write the code in a way that it adheres to it. All right, so we import from sklearn library datasets and model selection, and also the matplotlib library for plotting. We also load the iris dataset, which you can read more on this link. The first thing that we do is that we split it into train and test parts by using the function load_dataset. So we first load it, which contains data and the targets. We split the data into train and test parts, and then we return all of these parts together. And we want to do this split in such a way that we keep 75% of the data set for training. So this is where we are learning our model, and then we are testing in the remaining 25%. The first thing that we do is that we plot the data set. So this data set has 4 features. And we can then do 16 scatter plots where we show dependencies between each of the features. So the 4 features of this data set are the sepal length, sepal width, pedal length, and pedal width. So this is just to give an idea of this is whenever you have some data set, the first thing that you do is that you do scatter plots of each of the features, and you sort of want to see if they are relating to each other in some sense. Because if they are so much correlated with each other, then they might be fighting for significance. So you might want to remove some of the features in your studies. All right, so we have this iris data set. And now the first thing that we want to do is to implement the Euclidean distance between 2 data points. So as I said before, in this exercise, we want to make use of the norms where we want to compute the distance of a given test point to any other neighboring point. And actually, we are given 2 points x1 and x2. And the distance is a float. The Euclidean distance between x1 and x2 would simply be by using the linear algebra norm function. We could do this. And then we want to get the k nearest neighbors labels. So we are given now a new data point, and we want to classify this point with the label which has the closest neighboring point. So if you find another flower whose sepal width, length, sepal width are the closest to another neighboring point, then you just classify it according to the label of that neighboring point. But then first we need to get the labels of the k nearest neighbors of the new data point x new. And to do that, we are given some x train and y train data set, and we're given a new instance x new. We want to find the k nearest neighbors, get the labels of the k nearest neighbors. And we want to return an array which contains the labels of the k nearest. All right, so we begin by setting some space for these distances, which we then sort and look which one is the closest. Then for x's and y's and x train and y train. So in the training data points with the corresponding label, we compute the distance using the Euclidean distance function that we defined before between x and x new. And we append these distances to the distances variable that we defined before, and we also save their labels. So for a new point, we compute the distance to neighboring points, and we also save this distance and the corresponding label of the neighboring point. And the next thing that we do is that we sort these distances. So we want only the k nearest neighbors. Say them in some variable distances underscore sorted. So this is sorted. We want to sort the distances variable. And we want to do this only on the first object, so only by distances, and we want to keep the labels. And then we want to find only the k nearest neighbors. So we want now the entry on within this one, so the label, but only for elements of the tuple which contain the first k ones. And then we simply return this. All right, so then this function will return for us the k nearest neighbors and their labels. Labels, that is the same. All right, so then we computed the labels of k nearest neighbors, and then we want to know what class is actually the majority out of these nearest neighbors. So we define this function get underscore response, which takes the neighbors labels, which is an array with k elements containing the labels of the k nearest neighbors. And we want to return the majority class among the neighbors. So first we set some space for that. So among all the neighboring labels which have the same vote, so which have the same label, we increase this vote by 1. And then what we do is just we compute the vote which happens the most. So we want to know the label which occurs the most. And the final step is that we want to compute the accuracy of the generated predictions. So far we split the data set into training and test data sets. And we are using this train data set to train our nearest neighbor. We got a new instance of data, and we found the distance of this point to all the points in the data set. We sorted these distances to contain only the k nearest one and their corresponding labels. And then out of these k nearest neighbors, we selected the label which was occurring the most. So now we want to know how successful is actually this method is, because we actually have the true label of this new instance data that we want to classify according to this model. So then our final task would be to compute the accuracy for all these test data points that we have from the beginning. And for that, we define this function compute accuracy, which computes the accuracy of the prediction. It gets the predicted labels and the true labels. So we just have to sort of compare whether these two match. And if they match, then we say that we were successful. So we increase the accuracy by 1. So again, we loop over all y-pred and y-test points. In the cases that they result in the same prediction, we set the class correctly +1. And we finally want to return the average for all the data points. So class correctly is the number of correctly classified data points by our model. And we just divide this by the length of the total amount of y-pred points. And then as soon as we have this, we can also predict for all new points in the test set. So for any coming new test set, we can repeat the same procedure. All right, so finally we test this. Okay. Mistake. All right, so yeah, we get the accuracy, which is slightly, not slightly, but it's much more lower. All right, so yes, I mean, this classifier is not working so well. It could be also with the fact that we don't have so much data for this data set. But okay. Is there any questions so far on the nearest neighbors? I didn't read any in the chat.
I presume there were some questions on whether or not you can update the notebook, the correct solutions later.
Um, Um, alright. Enable label, I think it has different name. What do you mean the neighbor label has different name? From where? Okay, so I think I found the mistake. It was on the distance, and now it's the accuracy. It's 0.94. So yeah, the mistake for everyone who was following was here, that when I was appending these distances, we had a typo. But now Google Colab should all be working, and I think it has also all the solutions for everyone that is interested. All right, thank you very much for everyone that joined today. I hope to see many of you also tomorrow in the Calculus for Data Science lecture. And yeah, I don't know, do you have anything else to add, Uri?
No, everything's good. If possible, could you perhaps check the notebook and update it with the solutions, and I'll update the Colab notebook on the website later.
Okay, I mean, I think right now everything gets completed, but I can have another look. And
then that's perfect, and then I'll update the website with all the notebooks and today's materials.
okay, so thank you very much once again, and yeah, see you tomorrow then.
Thank you.
Bye-bye.